In this video, we are going to discuss topic 11.4, comparison tests. There are actually two tests in topic 11.4. The first test is called the direct comparison test, or sometimes it's just called the comparison test, as stated in Theorem 10. The other test in this topic is the limit comparison test, Theorem 11. We first begin with the Theorem 10, the comparison test. The idea is actually quite simple. Say you have a series that you wish to test for its convergence. I write this as AN. In order to tell whether the series AN is convergent or not, you try to think of another series BN, and then you compare the series A with series B term by term. First, you have to suspect or suppose whether the series you want to test AN is convergent or not. Now, if you believe that the series AN is convergent, then what you have to do is to think of another series Bn such that the term in Bn is larger than AN one by one, term by term, and at the same time, the series Bn is convergent. By the existence of another series Bn which is convergent, and at the same time all the terms in the series B is larger or equals to the terms in AN, then by the virtue of the comparison test, you will be able to use the convergence of Bn as an indication of the convergence of AN. You can try to represent this situation on a graph where you plot the two series on the plot of an xy plane, where the vertical axis represents the series AN and Bn. The x-axis is the index of n. We are talking about two series that are both convergent. In this case, first we have to represent the convergence of B. So imagine you have a B series, which I represent as a dot on this graph. So these dots represent Bn. And here Bn is a series that is going to be convergent. An, if is term by term smaller than the Bn, which I now represent as a green dot, then by looking at this graph, you could intuitively see that if the Bn, which is sitting on top of all the terms of An, and furthermore, if the Bn series is convergent, then all the points that is lying below Bn should also be convergent. Now let us look at the other scenario. Say again here, you have a series An which you want to check for its convergence or divergence. And if you suspect, for example, that the series An is divergent, what you do in this case is to think of another series Bn that is also divergent, but with the condition that the series term is smaller than the corresponding term in An. You can try to represent these situations by plotting both series on the graph. So in this case, you have an An term which is sitting on top of another series Bn, where the Bn point is below or equals to the corresponding An. So these represent the situations where the series A is larger than the series B, so that the An is always sitting above or equals to the corresponding point of the series Bn. And in this case, if the Bn is divergent, then all the point that is sitting on top of it, which is An points, should also diverge. Let me briefly conclude the comparison test as stated in Theorem 10. You are given a series, say A, where all the terms in the series is non-negative. In order to use the comparison test to test the convergence of the series A, what you have to do is to come up with another series B, where the series B would either be term by term larger than the series AN, and at the same time the series of Bn is convergent, or you come up with another series of Bn where the terms in the series is smaller or equals to the corresponding terms in An. At the same time, the series is divergent. So if you can find either a series that fulfill this condition or this condition, then you will be able to conclude the convergence of Bn. If, for example, you can find out any series Bn that is term by term larger than the corresponding terms in the series AN, and at the same time the series itself is convergent, then you conclude that the series AN is convergent. Or if you can prove the existence of a series Bn which is term by term smaller than An, and at the same time the series itself is divergent, then you conclude that the series Bn is divergent. Let us look at example 1. Example 1 is the series as shown on the whiteboard. In order to use the comparison test to check for the convergence or divergence of the series, you first have to make a good guess of whether this series is divergent or convergent. So to make a good guess of telling whether it's divergence or convergence, you have to be able to somehow recognize the series by comparing it with some other known series. So far, we have learned a few known series. The most important known series that we know of is what we call the harmonic series, which is known to be divergent. The other series that we have also learned is the so-called the P series. The P series will be divergent if P is less than 1 or equals to 1, whereas the P series would be converge if P is larger than 1. The other series that we know of their convergent properties is the geometric series. The geometric series will converge if the ratio magnitude is less than 1. If the magnitude of the ratio is equals or larger than 1, then it will diverge. So the first thing you do when you want to use the comparison test to check for the convergence of a given series, you try to compare it with some of these known series and try to guess whether the series that you are considering is convergent or divergent. So in this example, we are trying to first make the guess of whether each series should be a convergent one or divergent one by casting it to a form that is easy for us to make comparison with the other known series. With that, only then we will propose an series Bn to be compared with An. You pull out the factor of 5 upstairs and downstairs, then it becomes 5 times n minus 1 over 5. So that would be simplified to the sum of 1 over n minus 1 over 5. Now, if you have cast this expression of the series into this form, then it will give you a good idea of the behaviors of this series. The series that we have arrived at, An, has a form that could be compared with the harmonic series. The harmonic series is in the form of 1 over n. Here you have an series in the form of the sum of n minus n fraction. So this and this is comparable. They are both very similar, and if you look at this, you find that n minus 1 over 5 is always smaller than n. If you take the reciprocal of it, then you revert the sign from smaller to larger. So now we have a situation that says the term in the sum of an is term by term larger than the harmonic series. So imagine you have a graph that represents both series. The harmonic series is the green dot 1 over n, whereas these are an. So this gives you an idea that you have a series of an sitting on top of the harmonic series. So that is a situation where you can come up with a series Bn that could be used to be compared with the series of An. Here we will choose the series Bn as the harmonic series, and you can see quite immediately the series An is term by term larger than the harmonic series, and we know that the harmonic series is divergent. Therefore, by comparing the An series, which is expressed as this expression, when we compare it, CF stands for comparison, with the harmonic series Bn, which is written in this form. The series term An is term by term larger or equals than the corresponding term in the harmonic series, and at the same time we also know that the harmonic series Bn here diverges. Then according to theorem 10, this condition is fulfilled where D here refers to our Bn by the virtue of the item B in theorem 10. We say that the series An diverges. So to conclude this example, in order to prove the series to be divergent, you compare it with the harmonic series, and you prove that the terms in the series An is larger than the corresponding term in the harmonic series. So since harmonic series is divergent, then the series of An is also divergent. To show how we use the comparison test to check for the convergence of this series, let us first expand the series by releasing all the terms in the series one by one. Setting n equals to 0 give you 1 over 0 factorial. Setting n equals to 1 give you 1 factorial, 2 factorial, 3 factorial, 4 factorial, etc. If you compare this series with another series, a series which is made up of a geometric series with a ratio of half, where it starts to run from 0 up to infinity with an additional term of 1 added to it, then you write out the full expressions of this series, which we are going to call it the series of Bn. The series Bn will look something like this. If you compare the two series of An and Bn, you'll find that the first two terms in the series, Bn and An, appears to be the same, where the first two terms are equals to 1. For example, for the term n equals to 3, n equals to 4, etc., we are comparing the terms of An versus Bn, where we can express the An as 1 over n factorial, where n is larger than or equals to 2. Bn here is expressed as half raised to the power of n minus 1. If you compare, say, the n equals to 2 terms in An and n equals to 2 terms in Bn, we are comparing 1 over 2 factorial against half raised to the power of 1. If you're comparing the terms n equals to 3 in An, you are comparing it against n equals to 3 term in the B series, which is just half raised to the power of 2. And we want to argue that if you make this comparison one by one, An is always smaller than the corresponding term in Bn, where n term in An is given as n factorial. The terms in Bn is half raised to the power of n minus 1, where n is larger than 2. Writing down the series of An and Bn in this manner and making comparison For all the terms in an and bn, term by term, we find that the terms in the series bn is always larger than an and is equals to the terms in an when n is equals to 0 and 1, but for n larger than 2 or equals to 2, the terms in bn is always larger than an. Then we also know that the series as chosen here, the sum of Bn plus 1 is also convergent for the simple fact that the series Bn is a geometric series with a ratio of half. By virtue of the comparison test, we have found a series that is convergent and yet it is term by term larger than the corresponding term in the series we want to test for its convergence. By virtue of theorem 10a, we can then conclude that the series of an converges. Let me give a short summary of what we have learned from example 1a and 1b. Here you have a series an which you want to check for its convergence or divergence, and you know each of the term in the series an is positive. The trick of proving the convergence or divergence of a series an lies in whether you are able to propose any series bn that fulfill either this condition or this condition. If you can find, for example, any series bn that is convergent and yet it's term by term larger than an, then it means you have proven the series an as being convergent. On the other hand, if you can find any series Bn that is divergent and at the same time it is term by term smaller than the series An, that means you have proven the series of An to be divergent. In example 1a, we have shown the existence of an harmonic series which is divergent and yet it is term by term smaller than the corresponding term an in the series we want to check for its convergence. In this case, the existence of an divergent series that fulfill this condition here means the series an is divergent. In example 1b, we have proved the existence of another series which is convergent and term by term larger than the term in the series an we want to check for its convergence. Here is the series of Bn that is term by term larger than the corresponding term in An. Therefore, we have proven the convergence of the series An.